Hi everybody, so in this video we will be explaining why this sort of graphic of an apple falling from a tree and the claim that time dilation is what causes the apple to fall is not a visualization of spacetime curvature and why the time dilation is not causing the apple to fall. My background is I'm a graduate in physics and I've done one module on general relativity, but my main experience is I was also under this impression when I did my degree, and I was told by my professor that that is all wrong, and that hurt my head, and I was very sad for a bit, and then I did the course and I was very happy afterwards, and you can still appreciate what this diagram is doing without having to buy into the premise that time dilation causes the apple to fall, or that this is space-time curvature. You can still appreciate this diagram for what it is, which is actually a coordinate transformation, and these are pretty cool. You can appreciate these in their own right. So, for example, let's start with what the diagram will be showing. This is an apple, and we will draw a geodesic of the apple falling to the ground. And the claim is that the separation of these lines getting larger is time dilation, and it is because the time axis sort of curves away from the apple and the ground, or pulling the ground up with it, however you want to think about it, is what causes the apple to hit the ground, and that this apple is taking a geodesic. Now, the claim that I disagree with, and that was taught by my course as being wrong, is that this is time curvature. And this is not what this is. This is a coordinate transform. And that is important. So what we should do is define curvature. And curvature in geometry has a very specific definition, which none of these videos that I have seen actually discusses the definition of. Science Click is very good. They have a very good video on curvature, in which they actually define curvature. They don't use this specific graphic, and they do not make the claim that this graphic is time curvature. So I would say get some Science Click curvature stuff. That's very helpful. But curvature is a very specific thing, and it's to do with how vectors behave when you move them on a surface. That is it. That is, if the person talking to you about curvature will not give you this definition, then they are not talking about curvature in general relativity or differential geometry. They're using a different definition for a different thing, and they're making the mistake of saying that that is curvature. So this thing here, this is not differential geometry curvature. So when you see the titles that say, oh, this is time curvature, you're visualizing space-time curvature, they're using a different definition of curvature, which is not the one of space-time or Riemann or Gauss or whatever. They're not using that definition, and that is the issue which you will have if you go into a general relativity class thinking that you are visualizing curvature. So let's do a little parallel transport of a vector here on a long geodesics. So I'm going to move my vector this way, then this way, and then this way, and then it should stay the same. Oops, that is not the same. This would be roughly the same. And so we say this is zero curvature. Similarly, we will do a similar test where we have two geodesics, and do they diverge or converge? No, they don't. This is zero curvature. So why is this guy not curvature? Well, let's do a test. We can test to see if this graphic is actually curved. bear with me. There we go. We've got this. So let's start an apple traveling from here, and let's put it on its way. And this is a geodesic. And let's start drop an apple from a different height. And again, let it go on its way, and it will hit the ground. What about this distance between these geodesics? So what is the curvature of this spacetime that we have modeled in our toy? This is our toy model. These distances don't change. So this is zero curvature. And if you were to calculate the Riemann curvature tensor, all of its entries would be zero. This is very important if you want to understand general relativity and do a course or learn about the mathematics. It's very beautiful, it's awesome, but this is flat spacetime. If you want to see curved spacetime, you will have to draw a bigger region. So here is our small lab with a tree, and there's an apple. We need a bigger lab. We need the whole Earth. And we've got a tree here, and then here's an apple, and then here's a tree all the way over here in a different continent or whatever, a different country. And we want to see the curvature. And what you will see if you were to draw this diagram, let's draw it in normal coordinates, and we're going to draw some apples falling here. And then let's say we move to a different location. So this is number A, and this is number, let's say, or from a higher height. Let's say we drop it from a higher height. Let's go up here and drop our apple. Well, B is going to accelerate a lot more slowly, and then it will then fall to Earth. This distance is going to increase. So these geodesics will diverge, regardless of your coordinates. So these geodesics diverge. And this meets our definition of curvature. So this is curvature. We have found curvature. The issue with these videos that you're watching is that they will show you an image of the Earth, very big. They'll show you a nice curved manifold like this with some curved coordinates on it, but then they will zoom in. They will then zoom into this manifold, and then they will give you a toy model of a uniform gravitational field. And we have just established that this is not curved. Well, not at least curved in any sort of useful way that you would be able to see the curvature. It's there, but in this toy, they've zoomed over it. They've wiped over it. They've replaced it with a nice piece, nice fresh uniform gravitational field, which is good. We want a nice uniform gravitational field. It's useful for our purposes to model apples falling. But when they make this model, when they do their little diagram, it is not space-time curvature. It is a coordinate. This is a coordinate transform. And just because you use different coordinates, that does not mean there is curvature on your surface. For example, I'm going to draw a flat disk. Now I can use Cartesian to describe positions on this disk, or I can use, oh bloody hell, my pen stopped working. I can use polar coordinates. Now, just because I have changed, and just because these lines are curving, look at these, look how curvy these lines are. Look at those curvy boys. But does this mean that my disk is a curved surface? Well, no, it's flat. Look, I've drawn it on a flat piece of flat sheet. So there is no curvature. And this is the mistake that a lot of these YouTubers who haven't done a rigorous differential geometry course, or the person talk to them has glossed over this fact. I had a very good professor who was very clear on this. He rammed it into us down our throats. This is not curvature. Coordinates is not the same. It does not equal curvature. So what about the time dilation then? How can you have time dilation with a uniform gravitational field? So let's say you're on a rocket ship, because we're going to use the equivalence principle for this example to show you that even with the equivalence principle, there is time dilation in an accelerating ship. So I am a person, I have a light clock, the classic light clock of a photon. Well, let's make it blue. Blue, 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 blue. Boop, boop, boop. And then we have a red photon coming back down. Well, going up and then coming down. And then we have a clock. So if you were to do all of the calculations, it's been a while, apologies. I might do a video where I actually do the Pound-Rebka experiment, which is the confirmation of the equivalence principle. A very, very tasty experiment that proved the equivalence principle in a small local gravitational field that is uniform. You will get time dilation simply because of an accelerating reference frame. And there's no space-time curvature involved with this. This is just an accelerating reference frame. So when the people drawing these diagrams are saying that the time dilation causes the gravity, that is not quite correct. It is the accelerating reference frame which causes time dilation. It is the fact that you believe yourself to be in a inertial frame when you are not. When you are on the surface of the Earth, or when you're in a rocket ship, you think, I'm in an inertial frame, and there's a force of gravity acting on me. Actually, it is you are in an accelerating reference frame. How you choose to visualize that is up to you. The maths is the maths. You can try and visualize that however you want. The way that lets me sleep at night is to have a grid of space flowing into the floor of the Earth. So here's the Earth. And we've got a nice Euclidean grid. This is Euclidean. It's flat in a local area. And it's flowing into the Earth. And this will drag, let's say, an apple to the Earth. And that way, the Earth can be a non-inertial frame because it is accelerating relative to the grid, but the Earth isn't exploding, because then you can then the curvature kicks in. So now look, we are distorting. Now we're going to distort our grid and forget about the curved lines. It is the geodesics which will tell us whether this is curved or not. And as you can see, this geodesic is it's changing distance relative to this one. So this is how we know that space-time is curved. So yes, any questions, or anyone wants to make a follow-up video, anyone wants to do the Pound-Rebka experiment, just drop something in the comments. Let me know if you had the same idea or whether you think there's an issue with this. Bye.